we've got a cylinder bounded by this equation and by z from 0 to 6. This is obviously a circle of radius 2 in the xy plane, and then z goes from 0 to 6, so you just got this tube, okay? And you can calculate the area of its base. It's a circle of radius 2, so its area is 4 pi, and its altitude is 6, so its volume is 24 pi. Okay, well, that's easy. But we want to do things with this. We want to describe this region by inequalities, and you'll see where we go with it. Okay, inequalities in x, y, and z. Well, we can start with a picture. So your x values can go from -2 to 2. Okay, that's fine. Now you can say, okay, well, your y values go from -2 to 2 as well. Well, no, they don't. That depends on x. If y goes from -2 to 2, as well as x goes from -2 to 2, you got a square, you don't have a circle. Okay, so what's your inequality on y going to look like? Okay, so got a quick answer, that's good. And that's probably related to something you saw in your homework. So I'm glad you're picking it up in the homework and stuff like that. Okay, that's very good. Well, for given x, let's just take x right here. We have a given x along here. So x is how far it is from here to here, right? How far does y go? Y goes from here to here. And from here to here. Each of these triangles has dimension x here and 2 here, which means by the Pythagorean theorem that this leg is 4 minus x squared. There are other ways to do it. You could write it formally. You have the equation x squared plus y squared equals 4. If you assume that x is given, you solve this for y and you get the square root of 4 minus x squared. Same thing the triangle gives you. Is that clear? Don't want to spend too much time discussing that. Okay. So we can say that y goes from what? Well, it goes from negative the square root of 4 minus x squared to the square root of 4 minus x squared. And then z goes all the way from 0 to 6. And there we have a description of this three-dimensional region in terms of x, y, and z. So the partition region your x intervals go up to 2. And let's say they're n of them. And then your y intervals, well, your first y interval, for given about this. I'll get this. I'll write this coherent form. For the ith x interval, you're gonna have the square root of 4 minus x sub I star squared less than y naught equals y naught, sorry, which is less than y1 and so forth up to y sub. I'll call this m sub I. Which is then equal to 4 square root of 4 minus x sub I squared. So it's from negative square root of 4 minus x sub I squared to 4 minus the square root of x sub I squared. So in terms of the picture, it's as though we've got this partition. Here's an xi star in one of these intervals. And your y's are partitioned from here to here. These are your yj's. Each with a yj star. So if we take one of these intervals, one of these increments here, let's just take this one right here. And magnify it. Its dimensions are delta xi. Okay. Now, actually, I don't have enough subscripts on my y's. Okay, because for every I, you're going to have one of these y partitions, aren't you? Okay, so really I need to have like a yi0, yi1, yi m sub I. Okay, so you have now a delta y sub I m. Or, no, sorry, we'll do y sub I j. Okay. You know, delta y sub I j. When you have a sample point in here with with coordinates xi star yi j star, where I is the same as the index of x, and you have the I index on your y's because you have another set of yj's for each of these intervals in your x partition. And your x partition, of course, goes all the way from -2 to 2. Now, does that make sense? Okay. Well, that's great, but you know, we've been three dimensions here. Now we've got to stack your z partition on top of that, right? So now we have to kind of visualize this in 3 dimensions. So our picture is going to start looking like this. Okay, well, here's our circle of radius 2 in the x direction. Here's x, here's y, and here's z. And we've got our x partition here. And we've got a typical y increment. Our x increment. and it's divided up. And now we've got our IJ increment. In the plane. But of course, this goes all the way up to z equals 6. Now we can just kind of do this, and we can sketch our circle up here. So we've got our cylinder, and now we got the plane z equals 6. And we have these increments stacking all the way up. And I'm not calling this a whole lot of precision anymore. Never was. But now we've got the IJ stack of z increments. That makes sense? I is the index within your X partition. Maybe you've got it partitioned into 78 billion increments, and you've got number 38,297,586,482. Okay, there's your I. Okay. And then you're going to have a J. And then each of these will have a K. So here's your staff of Z. I'll call that ZIJK increments. You have IJ that narrows you down to this little increment in the XY plane. Now you got a stack here, right? Okay. And your typical increment there. There's your IJK increment. It's delta XI. Delta YIJ. And then delta Z. IJK. A little hard to write that in the space I have, but that's my attempt at it. And somewhere within this rectangular increment, we have a sample point. Ought to behave. There's our sample point. X, I, Y, I, J, Z, I, J, K, stars on it, and you probably can't read it. but I'll write it out. I'm gonna write out a Riemann sum. Okay, does that make sense? You can break it down like that, and now you have a complete description of the entire region. And you can just mathematically shrink these increments down as close as you want to points and get an expression for whatever you want. Okay, so that well, we complete our description of the region. For a given ij, xy increment, we have them zero less or equal to z ij one less than z ij two, and so forth, all the way up, all the way up to z ij k sub ij. And I don't really necessarily like my notation here, but it'll do for the moment. For k sub ij is the maximum value of k, you would have for the z stack that corresponds to the ij xy increment. Now you want to digest that, okay? And you're not going to digest it right now unless it makes perfect sense to you as I said it. But kind of store that away and make sure you understand that scheme. So that the total volume of all this stuff just for example, I'm going to use k for this. I didn't like it when I did it. I'll call this P sub ij. What do I write this one? Sorry. Okay, I start by summing my delta x sub i's. So for each one of these x increments, I'm going to sum all of the y's, and then within the y's, I'm going to sum all of the z's. So it's going to be the width of this increment multiplied by the delta yj's, that I sum up. And that's gonna be multiplied by and that should be J. Well, I'm being a little bit loose with my notation, but I'm gonna have to. I'm gonna be word too loose there. Okay, it would be this entire sum. So for every I and J, I add up all the Z's, all the delta Z's. Okay? And I multiply those by my delta Y I J, which gives me the volume of this stack. And then I add those up, J equals 1 to M sub I, which gives me the volumes of all the stacks from here to here. Okay? So now we've got this kind of wall built out of these little blocks. Okay? And it gives me the total volume within this strip. And I multiply that by the width of the strip. Well, when I multiply that by the width of the strip, I get the volume of the strip. And then I add up all those. Okay? This approaches the triple integral. Okay? And this would be from X. Of course, you know, okay, the inner integral is with respect to Z. Next integral is with respect to Y. Next integrals are with respect to X. And these integrals successively just do what I just said. They sum over these, and then they do stacks of these along here and so forth. And the limits on the integral from -2 to 2, from negative square root of 4 minus x squared to the square root of 4 minus x squared. And from 0 to 6 on Z. Our limits on Z, Y, and X are the limits that are determined by our partition. Okay, now fairly straightforward integral. Our inner integral is 0 to 6 with respect to Z. Well, that's just antiderivative of dz is just Z with limits 0 and 6. And then it's with respect to Y and with respect to X. That's just going to give you a constant 6, which we can bring out in front. And then with respect to Y, we get Y evaluated for the square root of 4 minus x squared negative square root of 4 minus x squared. And we'll be integrating that with respect to x. That's going to be 6 times the integral from negative 2 to 2 of two times the square root of 4 minus x squared dx, which is 12 times this integral. At this point, I don't want to get into the details. You're going to do a sign substitution, let x equal sine theta, or 2 sine theta, and do the trig substitution and do your details, okay? And that's straightforward enough. Each of these is going to give you a pi. You're going to get 12 times 2 pi, or 24 pi. Without going into the details, because we don't really have time to do that right now. Okay. And I expect you'll be able to do those details. Not difficult, just review something you knew quite well a year ago. Okay. And you probably already reviewed it to an extent. Did some homework. Okay. That's great. Well, that tells us exactly what we already knew. It's a volume of a right circular cylinder. There's no magic to it. It does give us, incidentally, the integral for the area of a circle. Okay, so if you ever forget what the area of a circle is, just do a simple integral and you find that it'll be pi over squared. Okay. In this case, it'll be pi times 2 squared. And you know, part of the 2 got absorbed there with this 2 and all that stuff. So not going to worry about that. Okay, well, that's fine, but now let's just say that you got this cylinder full of some kind of really thick syrupy concoction. Okay, it's denser toward the bottom than the top. Okay, so now and let's just say it's six minus z over 2. What's its total mass? Well, it's very simple to get an integral for the total mass. What's the mass of the IJK increment? That's all we need in the IJK increment. Well, we kind of obscured it here, so set it over here so we can look at it again, although you probably can't read it. So let me just, either IJK increment is what? It's your density at your sample point. I said I was going to write out the sample point coherently. I wrote it up here, but it's hard to read. Okay. But that's it. That should be obvious. If not, think about it, reconstruct it. Okay? That's the mass times the volume, mass density. You multiply mass density by volume, you get the mass. So that's then times delta xi, delta yi, delta z, I, j, k. What's the total mass? Well, we just write out movements. We just write out the same thing here. Okay. Except that we put our row of xi star, yj star, and all that in there. If total volume is the sum of all the volume increments. I'm just trying to figure out how to write the thing. Basically, I would think sum I equals 1 to n delta xi. Just gonna write out everything I've got here, except on this last term, I'm gonna write my density. Now, this last part of the summation is the first part, remember, that we're gonna integrate. Okay? The last thing we integrate is the delta x's because we have fixed limits. And if I didn't have fixed limits on the end here, I'd never get a fixed number. And certainly you've experienced that in the homework, okay? So we have this sum. Be a little bit careful and write it out reasonably well. Finally, here's where I write out my row of xi, yj, z, ijk stars. And I'm not actually going to write that out. Row of z is 6 minus z over 2. So this is just going to be 6 minus zij star over 2 times delta zij. And I'll just indicate that the row thing I've written specifically for this particular density function. Okay. Now this is then going to approach the interval -2 to 2. It's the same region, so the limits in the interval are going to be identical to what they were before. Except I'm going to have this 6 minus z over 2 in here. And then it's going to be with respect to z, with respect to y, with respect to x. And I can put in my signs of grouping if I want to keep it straight. So it's not a great big deal. Because again, the integral of the 6 minus z over 2 is just going to give you a definite number here. You're going to get 6z minus z squared over 4. You have weighted when z equals 6. Okay, it's going to be 36 minus And it's gonna be 32 and a half, I think, 33 and a half, something like that. But that's gonna take care of your row of Z. Okay? And you don't really have another good way to do it. Actually, you can shortcut it to some extent, but I'm not gonna talk about that. You know, get your feet wet and then have a shortcut. If your density was also a function of X, maybe it's warmer on one side of this container than the other, then that would complicate this integral, wouldn't it? Because you'd still have X's when you got through the first two steps of your integration. You'd still have X terms here, and your neat little pretty trig substitution, X equal 2 sine theta, isn't going to be so helpful anymore. Matter of fact, it might be so unhelpful that nobody can do the integral. And you got to approximate it. Okay? It just depends on your density function, the nature of your density function. It's a nice linear density function, you probably deal with it. But that depends on the geometry. What if this thing's an elliptical cylinder now? Okay? That complicates the details of the integration. It doesn't complicate the picture. It doesn't complicate the fact that if you did have an ellipse, okay, if it was x squared plus y squared over 4 equals 1 cylinder, elliptical cylinder, 6 units high or whatever. Okay. It wouldn't be very much more difficult at all to describe. Right? That makes sense? What you want to take away from this so far is that your ability to describe the region in inequalities is critical. If you can describe the region in inequalities, you can set up the Riemann sum and you can figure out what integral you ought to be doing. Now, whether you can perform the integral, I mean, most integrals that occur in the wild just can't be done in closed form. But there's so many important ones that can be done that it's worth learning to do your integrals in closed form. Now, what if we change? Okay, here's one twist we can put into this picture. Okay, another twist is let's just put some plane on the top of this thing. What's that going to do? Okay, what's that going to change? So what if is identical to what we have here, except that we're bounded above by the plane, some plane AX plus BY plus C equals D. Okay? Just some plane. Okay, but you don't know how it's oriented with respect to your X and your Y axis. It's got a normal vector. Okay? What does that change? Well, it wouldn't change much in this description, except Z would be now bounded by whatever your expression is. But of course, then when Z is no longer bounded by a number, but by something that depends on both X and Y. Have you got that kind of in your head? I can write out a specific example, but let's just kind of think it through for a minute. So let's just say it's 6 minus X minus Y. That's really simple. Okay. So it means above the origin, thing is 6 units high. Okay. And it could go down as much as 4 units and up to as much as 8 units, depending on what direction you move Um, it's gonna be an easy surface to visualize. So what does that do to your integration? Well, that introduces variables X and Y in for your Z, right? Which means you better not integrate with Z first. I take it back. It means you better integrate with respect to Z. Okay? If Z was 6 minus X minus Y, then you wouldn't get a 6 out in front here. You'd get a 6 minus X minus Y inside here. So that when you integrate with respect to Y, then you have to integrate that, and integrate with respect to X, you got to integrate that. Okay? Not a terrible complication, but it is going to complicate your expression when you get down to this. Okay, so let's just see how that works out. It's one thing to wave your hands at it, another thing to do it. Okay, now. Region bound by this, and Z equals 6 minus X minus 2Y, just to make it a little more variable. Okay. Then you have -2 less than or equal to X less than or equal to 2, negative square root of 4 minus X squared less than or equal to Y less than or equal to square root of 4 minus X squared, and 0 less than or equal to Z less than or equal to 6 minus X minus 2Y. So, etc. If you just trace through the steps, the only difference is that Z is going to go from 0 to 6 minus X minus 2Y. And you're going to get then the integral from -2 to 2, the integral from the negative square root of 4 minus X squared to the square root of 4 minus X squared, and the integral from 0 to 6 minus X minus 2Y with respect to Z, respect to Y, with respect to X. Okay. And this is going to then give you the integral from -2 to 2, the integral from negative square root of 4 minus X squared, the square root of 4 minus X squared of 6 minus X minus Y minus 2Y dy dx. Then integrating this with respect to Y, we get the integral -2 to 2 of we get this. Okay, then we want to make sure that we don't confuse our x's, confuse our integram with what we're integrating with respect to and so forth. So it doesn't hurt to put a y equals here. Remind ourselves that it's y that's equal to this, so we have x's and y's through here. So we don't actually accidentally substitute this for x, you get a y. And our final integral should make no sense. Okay. And that's going to give us what? Integral from -2 to 2 of going to be 12 times the square root of 4 minus x squared. Same thing we would have gotten over here if we'd have done it that way. And then it's minus xy. Well, then that's going to be minus 2x times the square root of 4 minus x squared. That's going to be minus y squared over 2. But fortunately, y squared is going to be the same here as it is here, since you're squaring. Doesn't matter if you have a positive or negative. So you're going to do the value here minus the value here. It's going to give you 0. And this isn't bad. You can still do this by your trig substitution. And then here you just let u equal 2x and you got a du. Just straightforward substitution, right? So both these integrals would be quite easy to do. Now, if it was a square root of x here, that could complicate life. Okay, it doesn't take much to complicate life to where you get an integrand that you can't perform. But in the case of the examples we've done so far, the integrals are straightforward. Okay, that makes sense. Well, okay. So that's like volume integrals using rectangular coordinates. And that's section 4. It gets more complicated. What if you have a sphere? How do you describe a sphere? Well, you should be able to do that. You can do if you can do a circle in 2 dimensions, you can figure out what to do with a sphere. Okay. And we can talk about that if we have time, but I really want to talk about polar coordinates, because that leads directly into the volume integrals you get when you're in cylindrical and spherical coordinates. And you're going to have trouble understanding that unless we have pretty solid understanding of polar coordinates. So let's move polar coordinates. First of all, we'll do a polar region, 0 less than or equal to r less than or equal to 2. And zero less than or equal to theta less than or equal to 2 pi. Now, what is that? What is that region in the plane? Okay. Look, as a revelation, this is the same circle that we just dealt with previously, right? Except we're going to do something a little differently. Maybe this is the cylinder. Maybe it extends up to z equals 6. In which case you'd have a cylindrical region and cylindrical coordinates, wouldn't you? Okay, yeah, very simple description. Probably be simple to integrate it. Okay, now We want to do density. Um, density 1 plus R. And this is actually a surface area region, okay, surface density. Usually for a surface density, we wouldn't use rho. We'd say rho or volume densities. And of course, that leads to complications if we're in spherical coordinates, since rho is one of our. Anyhow, okay. So I'm gonna let sigma of R, it's like a surface density. But the idea is we just multiply sigma of R times an area and we get the mass. Okay. So we find the mass of the disk. Describe the region. Or not, let's got our description pretty much. Actually, we don't. No. It's obvious. Okay. Zero, R from 0 to 2. Theta from 0 to 2 pi. Our partition. R1 goes from 0 to 2. I didn't think I said that right, but okay. R naught less than R1, et cetera, up to less than Rn, which is 2. Theta naught equals 0, not theta. And that's less than theta 1 up to theta sub m, which is 2 pi. A picture, very simple. Not that easy to draw. Here's like our R axis. And we partition the R axis from 0 to 2. Each of those partitions corresponds to a ring, because of course theta goes all the way from 0 to 2 pi, right? So theta can be any angle. So all the points between R n minus 1 and Rn lie within this ring. Then our theta partition is going to give us something like this. And now our typical increment it's like our delta Ri by delta theta J increment. Now, what are the dimensions of this increment? What's the area of this increment? Well, from here to here is your delta R. So this distance is delta R sub I. And it's the same over here. Of course, these aren't exactly parallel, but what's the width of this thing? Let's take our sample point, Ri star theta J star. The increment is delta Ri long this way. It's not a perfect square, is it? Because, you know, constant theta keeps flaring out. The further out from the origin, the bigger it is. Okay, the wider it is. How wide is it? Well, we measure its width here. So what can you tell me about the width at this point? Point Ri star theta J star. In terms of a delta theta and a delta R. If we look at, let's say this dimension here, it's pretty much the same as an arc. So you have a circular arc around here. And it's a little part of that circular arc, isn't it? Well, what's the arc distance on a circle in terms of your delta theta? By the definition of a radian, you multiply the radius by your angle. That's the definition of a radian, and I want you to really look that up and really reconcile that. With the definition of a radian. Because people keep losing track of it. Nobody ever remembers what the definition of a radian is. It's an angle such that the arc equals the radius. Such that there are 2 pi of them around the circle. And for that reason, for any angular discrepancy here, your arc distance is equal to the arc times the radius. And since, as this thing, since as we let everything approach 0, this is going to approach a straight line because your angle is going to shrink down to 0. And that's the dimension you use for the width. So that the area is there's your area increment for polar coordinates. Okay. area of this region is okay. Area is this. And that approach is just a double integral. R is partitioned from 0 to 2. Theta is position with a partition from 0 to 2 pi. And well, I have to write the theta dr, but it doesn't make any difference. You do r d theta dr, do this integral equals integral 0 to 2 of r times theta evaluated from 2 pi to 1 to 0 or dr, which equals the integral from 0 to 2 of 2 pi r dr, which is 2 pi times r squared over 2 evaluated between 2 and 0, which is 4 pi, which is the area circle radius 2. Okay. Now, if you have a density function, well, for each increment, you multiply the density by the area. Okay, density times the area of the increment. And this approaches the integral from 0 to 2, from 0 to 2 pi of 1 plus r times r dr, r d theta dr, because I've got my theta integral on the inside. Okay, well, this is just r squared over 2 plus r cubed over 3. And I'm integrating my r early. I'm going to do that. Right now, we're just integrating theta. So I'm going to call that r squared plus r times theta, again, between 0 and 2 pi dr. That's going to give us a 2 pi out here, and it's 2, not 2 pi there. Gives a 2 pi here, and then it's times integral from 0 to 2 of r squared plus r dr. which is 2 pi times r cubed over 3 plus r squared over 2 between 2 and 0. And that's going to be what? 8/3 plus 4/3, which is 12/3, which is 4. And I think that comes out 8 pi. Little question mark on that because I did it kind of fast. Now, my point is that once you understand the summation, which you understand by understanding the partition process, and once you understand what goes into the typical increment, which is density times area, your integral just falls into your lap. Then you just have to have integration technique to do it, if it's possible to do it, and it makes sense to know when it's not possible, which is the tough part. Takes a lot of sense.